Welcome to note set number 35, where we're going to take some of these ideas, frequency response, transfer function, pole zero diagrams, and use them to analyze actual continuous time filters that you might run across in some actual circuits. These will all be passive filters. Later we'll take a look at a couple active filters, but whether they're active or passive, the basic ideas are the same. So we've already talked about ideal filters and asked what we want out of the magnitude response and what we want out of the phase response. And we also saw that we couldn't really get these ideal filters. We would need a non-causal system to do that. So we're going to take a look at what kinds of simple filters we can actually make. And all continuous time filters exploit the fact that capacitors and inductors have impedance that's frequency dependent. And as I said, the tools that we're going to use are what we've been looking at: transfer function, frequency response, pole zero diagrams. And just pointing out that for discrete time filters, remember, we were limited to minus pi to pi radians per sample. For continuous time filters, we're looking at the full range, minus infinity to infinity, and the units of the frequency are radians per second. And we're going to mostly plot them on log frequency axis. We've talked about that before, and we'll plot the magnitudes in dB. So before we get into that, let's just talk about how someone might request a specification for a filter. And I'm showing just two possible different ways of speccing a filter. I'm sure there are some others, but these are the two main ones. This looks a lot like the discrete time one that we saw, except the main difference is it doesn't stop at pi and continues going up on up. But we still have, we have all the other things: pass band, transition band, stop band, specification of level in the stop band, and ripple in the pass band, and so forth, and what we need to do to make these things more ideal. A second format for speccing these things is to specify a cutoff frequency, which, and I'm showing these things here for the low pass version, but there's versions for, you can do the same thing for other types of filters. So the cutoff frequency is defined to be the point where, if our pass band is at 0 dB, where do we drop to minus 3 dB? If our pass band happens to be at some other level than 0 dB, we want to go to the point where we drop 3 dB. So it's often called the 3 dB down point. And so those are that's our one main spec, is where is the cutoff frequency, and that defines the pass band. And even though it dips down a little bit in our defined pass band, we're saying that's okay. That's what we're speccing here. And then the other spec is how fast this falls off. Now notice I'm doing this on a log versus dB plot. We spec these filters in terms of how much dB change do we have over a decade. So a decade is a 10x change. Now sometimes you'll hear about the change in dB per octave. An octave you might think is an 8x change, but it's not. It's actually a 2x change. I know it's weird, but that's just how it works. So for discrete time filters, we talked about how there's two different categories: IIR, FIR. CT filters don't have that same categorization because they all have infinite duration impulse responses. So instead we categorize them according to how they're built. Passive versus active. So passive filters are just made out of resistors, capacitors, and inductors, and there's no active components, like no op amps, no transistors, none of that stuff. And one of the main advantages of a passive filter is you don't need any power for it. You just stick it someplace, and the signal going through it will be filtered. Now, active filters, you do have to provide power to bias the transistors and power up those op amps, but they do have some advantages. You can actually design active filters with just resistors and capacitors, and there's no need for any inductors. And that's good, because inductors are frowned upon in miniature electronics. But you can also use op-amp and transistor characteristics to allow a simple cascading of several of these stages, so that you can design each stage independently without worrying about its impact on any stage prior or subsequent to it. And that's because of the large input impedance and small output impedance that op-amps have. And we will look at an example in a later video that talks about that. Okay, so this is just going to be kind of a garden walk, so to speak, through a variety of different RLC type circuits, so that we can get a feeling for what kinds of things we can get. And we'll be starting with the circuit diagram, deriving its transfer function, looking at pole zero plots, and trying to get a feeling for how these things behave. So we've already analyzed this circuit a number of times throughout the course, and we've already seen that it is kind of a low-pass filter, but we're going to take a look at it here with some of our new tools. So just like before, we're going to do our S-domain analysis. So inputs, inputs and outputs. I guess I should have called that X. Inputs and outputs will be replaced by their Laplace transforms, and components will be replaced by their S-domain impedances, and then we just use any DC circuit analysis tricks that we want to solve for Y of S in terms of X of S. And then the thing that ends up multiplying X of S, that's our transfer function. So if you do a voltage divider here, is the easiest. So you take this impedance divided by the sum of those two times the input. So there's our transfer function, H of S, but we want to get it in the terms of a polynomial in S. So if we multiply top and bottom by CS, then we get something that looks like this. And then the last thing we want to do is make the highest power have unit coefficient. So now we multiply top and bottom by 1 over RC, and we get the form that that we would prefer. So this is our transfer function. All three versions of the transfer function shown here are all equivalent. They're just algebraically equivalent versions of this, but this is the standard form. And so we look at that and we see, okay, there's a first order polynomial in the denominator, so that gives us one pole, and we can see where that pole occurs. It occurs at S is equal to minus 1 over RC. And so we immediately see, okay, it has this pole is in the left half side of the plane, so we know that this circuit's going to be stable. But we knew that already. All passive RLC circuits are stable. We know this is first order, so that's all we've got is one pole. So there's the pole zero diagram. And notice that as I increase my RC time constant, the pole moves towards the origin. And as I decrease my RC time constant, my pole moves further from the origin. So remember, a low RC time constant means that the circuit can respond very fast to transients. So let's keep that in mind as we analyze this. So this just repeats up at the top a few of the transfer function that we had, and since it is a stable system, we can replace S by j omega if we wish, and immediately get the frequency response, and that's the frequency response that we've gotten before. And you'll notice there that now I've gone back from that standard form I didn't necessarily have to, but sometimes it's more convenient to write it in frequency response outside of that standard polynomial form that we would get from S. And again, we see the effect of this or one of the roles of the RC time constant. If we look at 1 over the RC time constant and say when omega is equal to 1 over RC, then we get this term here becomes 1, and we get 1 over the square root of 1 plus 1, so the magnitude becomes 1 over square root of 2, and in dB that becomes minus 3 dB. So if you remember, that was how we defined in our spec the cutoff frequency of a low-pass filter. So 1 over RC is equal to the cutoff frequency, and so the pole in this example is located at negative the cutoff frequency, but on the sigma axis. So you start seeing some weird things. You would think cutoff frequencies would somehow interact with the j omega axis, and we will see that they do, but they also have a role on the sigma axis. So some little mind-bending things happen here a little bit. So for a simple RC low-pass filter like we've seen, the cutoff filter or cutoff frequency is 1 over RC. So if you want to design one of those, you just choose an appropriate R and an appropriate C so that your 1 over RC gives you the cutoff frequency. And this is in radians per second, so if you want it in hertz, you would have to divide that. So FC in hertz, cutoff frequency in hertz, is 1 over 2 pi RC. Now, if you've ever played with any electronics or done any hobby electronics, you may have seen that formula show up as a design equation someplace or other. Now you know where it comes from. So let's take a look at this for two different RC values, two different cutoffs. So for omega C equal to 1,000 radians per second, so we have a pole way out there, and we see that the cutoff happens at 1,000, right? So remember, this is being plotted. We're slicing across along the j omega axis and looking at the magnitude plot over that S plane, and this is what we get. And then if we look at it for the other case, where the pole is much closer to the origin, we see that our cutoff frequency moves back here. So kind of the interesting thing is that the further we move this out, this direction, not on the j omega axis, the further out our cutoff goes on the j omega axis. So it's kind of a weird thing, but that's what the math does. Math is often our best defense against weird operations. And this is just some MATLAB code that tells you how I went about making these nice plots. And you can see I'm using freaks, and I specified my cutoff frequency, and I used that up here. So I had in my numerator I had WC, in the denominator I had 1 in WC. So that's a nice way, and you can see that I'm doing semi-log x to get the log axis, and I'm doing 20 log 10 absolute value of h to get the magnitude. Excuse me. And then the other thing is that I created my frequency vector with a command called log space. And what that does is it gives me points that are equally spaced on the log axis. If I were to just use equally spaced points, they would be widely spread down here and then very closely spaced up here. So I don't want that. And so log space, I put in the lowest power and the highest power. So 10 to the 1 and 10 to the 5. And then 1,000 gives me 1,000 equally spaced points between those two extremes. So it's a very nice little command to have available. Okay, let's take a look at a first order high pass filter. Still an RC circuit, except what we've done now is exchanged the roles of the R and the C. And so now let's analyze that. There's our Laplace version of the circuit, dual voltage divider. The denominator is the same because it's the sum of those two things, but the numerator now is R. So for the low pass filter we had the 1 over CS up there, but now we have just an R. And now we do the same algebraic tricks and we clear that, and voila, we get an S up there. So again, it seems backward. Our voltage divider doesn't give us an S up there, but we end up with an S. Whereas for the low pass version, we start with a 1 over S up there, and we end up with no S at all when we're done with our algebra. So nonetheless, what we're seeing here is that for the high pass filter, we have a 0 at S equal to 0. So that lies right at omega equal to 0 on the j omega axis. And we'll see that's what ends up causing this to be to not pass low frequencies. And we get the same exact pole. We get a pole zero diagram that looks like this. So for the low pass, we had just this pole and we did not have the 0. For the high pass, we've got a 0 there. So now remember, we're going to find the frequency response, we cut along the j omega axis, and look what happens. That 0 ties down the frequency response to 0 at omega equal to 0, and therefore it keeps it low at low frequencies. And so that's exactly the behavior that we want from a high pass filter. So let's take a look at this a little bit farther. Okay, there we go. So I've just repeated what we had here. Again, I have a stable system. Poles are all on the left half side of the plane. No surprise, it's a passive RLC circuit. I go from this version and I replace S by j omega, and so I get a nice form for my frequency response. And then I can take the magnitude of that. So the magnitude at the top is just RC magnitude of omega. Magnitude of the bottom, same kinds of things that we've seen before, square root of the sum of the squares, and so we get that same thing. And again, we see that the magnitude drops to 1 over square root of 2, which is minus 3 dB, precisely when omega is equal to 1 over RC. So that cutoff frequency is set again by that pole position, the pole being on the real axis, the sigma real axis. So if we continue on here, we see that we get a structure that looks like this, where this is our cutoff frequency, and the cutoff frequency is defined as 1 over the RC time constant. So just like before, now I'm doing some MATLAB commands there, and because of the S in the numerator, I have to have a 1, 0 there to account for the fact that I have S plus 0 in the numerator. Excuse me. Sorry about the coughing. And so now what we're seeing here, as we have a pole all the way out here, that's pushing our cutoff frequency further out to the right, just like before, except now instead of coming across and dipping down, the cutoff frequency happens in the opposite way. We're coming up and then it levels out. And now if we move our pole closer to the origin, to 1,000, minus 1,000, now we have a cutoff frequency here. So moving it this way moves our cutoff frequency this way, moving it this way moves our cutoff frequency out that way. Very interesting behavior. It all shows up in the math, and we've gone through that math. And just like we saw for the low pass filter, the slope out here, we're seeing plus 20 dB per decade. If we go back and look at our slope for the low pass filter, it was minus 20 dB per decade. But the important thing is that it's a change of on the order of 20 dB per decade, going down obviously for low pass filters and going up for high pass filters. So that value, 20 dB per decade, whether it's up or down, is an important one, and we'll see in a little while, I think in the next lecture, where that 20 dB comes from. So there we're moving the pole closer to get the other behavior. Okay, so let's just take a quick summary of this low pass and high pass. And one thing you should start getting familiar with is, before you even do any mathematics, just try to look at the circuit and get a feeling for what you think it is going to behave like. And all you have to do is remember that capacitors look like short circuits at high frequencies and open circuits at low frequencies, and you can see that from the 1 over j omega c behavior. And inductors are the opposite. Inductors act like short circuits at low, so they're j omega L. So they act like a short circuit at low frequencies and like an open circuit at high frequencies. Here, knowing that at high frequencies C is like a short, so at high frequencies this gets shorted across and our output is 0. So that tells us that high frequencies are stopped or highly attenuated. And then at low frequencies this acts like an open circuit, and so there's no voltage drop across this, and so we then have perfect passing of low frequencies. So if you can analyze circuits, kind of seat of the pants like that, it provides great abilities. Again, sorry about that. One thing that we've seen is that by moving this pole back and forth, we can move our cutoff frequency. For the high pass filter, again, at low frequencies the capacitor is like an open, so this is just broken and no voltage can get to the output, so it stops low frequencies. And at high frequencies it's like a short, and so in that case it's just you're connecting the voltage directly to the output, and so you have a perfect passing of the high frequencies. And again, just summarizing the results that we've seen and recognizing the effect of changes in RC time constants. So notice that let's talk about the low pass case. We're used to for this circuit, the RC time constant, if it's small, we say that it can respond rapidly to transients. Well, when it's small, the pole has moved further out, and when the pole has moved further out, our cutoff frequency is even further out. And so what that says is, to pass, if we want a circuit to respond rapidly to a transient input, we want it to pass very high frequencies. And we've seen that idea before too. Input signals that have rapid changes contain high frequencies. Therefore, to get those rapid changes through the filter, we want it to pass high frequencies. So a lot of these ideas are starting to come together and make sense here, hopefully. All right, let's go to a second order circuit. And the reason that this is second order is that it's got two energy storing devices. It's not always true. Sometimes you get a degenerate structure, but for the most part, if you count how many capacitors and inductors you have, that will tell you the order of your circuit. And the higher order you go to, the more capability you have in making that circuit do, to make very high performance filters. So let's look at this. We're very quickly jumping over to our Laplace version of this. We're going to write the voltage divider for this. Now sometimes voltage divider doesn't work, but the cases that I'm looking at here, and really a lot of stuff you do in the real world boils down to just being able to do voltage divider. So you really ought to have that under your belt. Now we do a little bit of algebra, clear all the S's out of the bottom, and we get something that looks like this. So we see that we have a constant in the numerator and a second order polynomial in the denominator. Now it's sometimes helpful to have a general characterization of these second order systems. So this form that I'm showing here is a very general form that shows up for lots of different systems, not just RLC circuits. So omega sub n is called the natural frequency, and again this square box should be equals with a delta sign over it. That means defined to be. And the damping ratio zeta is defined this way. So the omega sub n squared is the square of the natural frequency. We come over here and we see omega sub n squared is 1 over LC. Therefore, omega sub n is 1 over the square root of LC. And again, if you've designed any circuits following some design rules, this 1 over square root of LC thing you've probably seen before if you've dealt with any RLC circuits before. So we'll explore what these damping ratios and natural frequencies tell us about the behavior of this circuit as we go through this. Now, coming back to here, we see that we've got a second order denominator. So that means we've got two poles, and there's three possible ways that we could have two poles. So the first way is they could show up as complex conjugate poles. So they're off the sigma axis so they don't lie directly on the sigma axis, so they have some complex part to them. Another way is that they're real, but they're repeated. So both poles are at the same place. That would be when we find the roots of this and we find out that we have a double root. And then the third possibility is that we have two real poles and they are distinct. So since they're real poles, they will lie both lie on the sigma axis. There's no way for a real-world circuit to give you one pole on the sigma axis and one pole that's complex. Just simply can't have that case. It just comes out of the mathematics because the R, the L, and the C give you real coefficients here. So all real coefficient polynomials end up having their complex roots appear as complex conjugates. So let's look at this a little bit farther. We can use the quadratic formula to write out the roots. So these are the positions of the poles, and we can see that R, L, and C show up, and in particular one of the parameters is R over 2L, and the other parameter is 1 over LC. Let's go back and look at that. R over 2L, that's our damping ratio, and 1 over LC is actually our omega n squared. Now notice that shows up inside a square root, right? So these damping ratios and natural frequencies define something about the poles here, as we'll see. So let's look at these three cases that we could have. Complex roots will occur whenever the thing inside this quadratic ends up being negative, because then we'll end up taking the square root of something that's negative and we'll get an imaginary part. So this would be the real part of the root, and then we'd have the imaginary part. So that happens whenever this condition holds. So when our resistance is really small, so a low resistance is going to cause us to have complex roots. And in fact, if we could make the resistance 0, which in practice we can't because the wires will have some resistance, the inductor itself has some resistance, the capacitance has, a real-world capacitance has some resistance, so we can't really do that. But in theory, if we could make it be equal to 0, then what we see is that the poles are on the j omega axis. So these poles would actually be lying right there on the j omega axis. But we can't get that in reality. We could get close, perhaps. Second case, repeated real roots. Well, that's going to happen when this thing is equal to 0. And so that happens precisely when R is equal to 2L over the square root of LC. And yes, I could cancel a square root of L out of there, which would then, this is equal to 2 over the square root of L over C. Same thing. I chose to leave it in terms of square root of LC since that has a physical interpretation as the 1 over the square root of LC is omega sub n. And this, if you plug this value of R into the equation for our damping ratio zeta, you'll find this has a zeta of 1. And coming back up to the complex root case, if you plug in an R in this range into the zeta formula, you'll find out that you have a zeta less than 1. And zeta will be greater than or equal to 0, obviously. R equal to 0 gives you a zeta of 0. So R is, you can think of in this circuit, R is the damping factor, or the damping mechanism. So setting R too low, you have what's called low damping. Setting R really high, you have what's called over damping. And when R is set so that zeta is equal to 1, that's called critical damping. So it's not important that you necessarily memorize that, but you should be aware of that. Again, that would be a nice interview question, but only for somebody who's really applying for a job in analog circuit design or control systems. So anyway, in that case, we have 2 poles that are on the sigma axis. And then the final case, as we increase R even farther, so that now R is greater than 2L over square root of LC, then we get a zeta greater than 1, and that gives us 2 distinct real roots. And so we would have 2 roots both on the sigma axis, and it would look like that. Now it's interesting to watch the path that these roots take as we increase R from 0 up to some larger value. So if we started R equal to 0, zeta equal to 0, we would start with 1 pole over here and 1 pole over here, right on the j omega axis. Note that this is essentially dangerously close to being unstable, and in fact such a circuit is called marginally stable. So anyway, the poles start there, and then as we increase R, and effectively at the same time increasing zeta from 0, so as zeta goes from 0 to just shy of 1, the poles follow this path. So we increase R a little bit and we might have poles that look like that. Increase it a little bit more and we'll have poles there. So I've made a plot here of letting R run over a fairly fine grid of points, and you can see how it moves following this path. And then finally, just as you hit R, setting it exactly equal to this value, you get zeta equal to 1. Those 2 paths converge and you get a double pole right there, just for that one specific value of R. Now as you increase R a little bit more, you get zeta greater than 1, and you get 2 things happening. So one of these goes this way and one of them goes that way. Now you could say, how do I know which one goes which way? I don't. I just chose to make that association. But once they hit together and they're combined as a double root there, you don't know which, quote unquote, which one is which. But the point is that then as you increase R further, you get one pole that moves towards the origin and you get another pole that moves away. Now there is a point where it won't go any further, and that depends on the component values of L and C. So anyway, you can see that for this one circuit we can get quite a bit of different behavior. If the poles are complex, we'll get one type of behavior. If they're repeated, we'll get another type, and if they're real and distinct, we'll get yet another entire different type of behavior. So here's the 3 different types of behavior that we can get. They're all low pass, but they all 3 have a slightly different characteristic. So let's cycle through these. Let's talk about complex poles first, with our damping factor zeta being less than 1. In this case, I've chosen my LC so that my omega sub n is 5,000 radians per second. And you'll notice that I've drawn a line here at 5,000, right? There's 1,000, 2,000, 3,000, 4,000, 5,000. So we're looking at this case. There's our poles. Our poles are at minus 500 and plus or minus J 4979. Okay, so that's where the poles are. So they're out here. Those are the poles that we're talking about, and we get this green curve. Notice how close the poles are to the j omega axis. So this is the j omega axis. Shame on me, I didn't label my plot. This is the sigma axis. We can then see that when the poles are close to the j omega axis, we get this spike, this peak, and that's called a resonant peak. Not resident, resonant. But some other things we can see is that down in our low frequency passband, it's nice and flat at 0 dB. It peaks up, but then it drops back down, and we see that the peak occurs pretty close to omega sub n. And we see that our cutoff frequency is somewhere out here, which is just a little bit above omega sub n. And then the other thing that we see, and this is for a zeta equal to 0.1, so that's a pretty small damping factor. The other thing we see is that eventually, once this thing gets out a ways, it does turn back into a straight line on the dB log scale plot, and its slope is minus 40 dB per decade. Remember, for the RC low-pass filter, we had only minus 20 dB per decade. So now we see that we've got the second case, repeated poles. Now we see that we get, again, something happening right around omega sub n. We're actually down 6 dB there, so backing off a little bit, our cutoff frequency would be somewhere around here. So technically our cutoff frequency is a little bit to the left, but it's still kind of behaving the same way, and we still see this minus 40 dB per decade behavior. And then, and that's for the case where we have repeated poles right there. So these things have come like this, and now they're going to split. And notice that after the split, the one moving towards the origin doesn't move very far, and the one moving away from the origin moves quite far. So they don't have the same rate of motion as each other. And then, so for that case, now we have two things that are happening. So we have a root at minus 858, and we have a root at around minus 30K. So two things happen here. We can think of this as being the cascade of two first order systems, and so that first pole at 858 is pretty close. Well, that's where I have this red line, and we can see that we get a minus 3 dB point there. But then for a little while we're going minus 20 dB per decade until we hit the second one at around 30K right there, and then we get a transition to minus 40 dB per decade. Now, don't worry too much about understanding all that. I think in the next video or very soon we'll be talking about Bode plots, where we'll have an ability to understand this a lot more than what we're seeing here. But the big idea is that second order, except for the case where we have the distinct real poles, for the other two cases, right off the bat we're getting a minus 40 dB per decade. For the distinct real poles, we do eventually get that, but we did have to suffer a minus 20 dB per decade first. But what that's telling us is that the higher order circuits we go to, the faster we can roll off, and the faster we roll off, the better this looks like an ideal filter. So ideally we would like a very large roll-off rate here. So that tells us something. Let's look at a second order high pass filter. We're switching things around. We had the capacitor here before and the inductor here. Now we've swapped those. And again, I encourage you to think about these in terms of, at high frequencies we do this, at low frequencies they do that, and so on, and see if you can puzzle out why they're high pass and low pass. We do the same thing. I'm not even showing the Laplace circuit anymore. We should get to the point where we don't even really need to show that. We do our voltage divider, we do a little bit of algebra, and we get this. Now notice we've got the same denominator polynomial, but now we've got an s squared up there. Before we had a constant. So let's see what that looks like. We can define same things. Our natural frequency as the square root of that. Our zeta, once we know what this is, we can easily find what zeta is by looking at that quantity. And we'll go through an example at some point. Again, three possible ways of doing this to handle these two poles, but now we've got two zeros at the origin. So we could have complex poles, we could have two repeated poles, or we could have two distinct poles. Now, the thing that's common in all of these is a zero at the origin. So when we're slicing through at the j omega axis, notice that in all three cases, those two zeros are really tying the frequency response down at low frequencies, and that's what makes this a high-pass filter. So here's our three cases. I'm going to go through this a little bit faster than the previous one because I see we're already up over 40 minutes on this video. Maybe I'll split this into two. I don't know. We'll see. And so it's the same kind of thing, but we're seeing this 40 dB plus 40 dB of slope out in front. Now basically we can count on 20 dB of slope in a low pass or a high pass filter, 20 dB of slope for each order. So if we had a third order low pass filter, we could count on minus 60 dB minus 60 dB per decade of roll off in our stop band. So the higher order you go to, the better your filter is going to be. But that means that you need more energy storing devices. So you're going to need 3 LCs. They don't have to all, like two capacitors, one inductor, 2 inductors, 1 capacitor. You might be able to figure out a way to do it with 3 capacitors, but you certainly could do that for an active case. And then finally, here's a second order band pass filter. This is a RLC circuit, and so now I've got the resistor here, and again I encourage you to puzzle your way through and see if you can figure out just from the circuit behavior. Again, we do the same kind of thing, end up with exactly the same thing in the denominator, but now we have just a single S up in the numerator, and we notice that it's 2 zeta omega n up there. Our denominator has the same definitions of natural frequency and damping ratio. Again, 3 ways to get the poles, same kind of idea. And now we get something that's kind of interesting here. The center of the activity here is at 1 over LC, and in this case I chose 1 over square root of LC. So my natural frequency is 1,000 radians per second for this example, and so you can see that that sets the center of my band of my passing. And you can see that when I have a small damping ratio, I end up with a very narrow spike that passes things. So sorry, if I only want like a very narrow band to pass, that would be the kind of filter that I would want to design. Notice here, though, if I want to pass a broad range, like maybe have this be some sort of audio range, 20 hertz up to 20 kilohertz, and stop very low frequencies and very high frequencies, then I would want the case where I have distinct roots, because it comes up, then it goes flat for a while, and then it goes back down. But notice that each and every one of these things has a slope of plus or minus 20 dB. So 20, 20, 20, minus 20, minus 20, minus 20. We've got a second order system, so why aren't we getting the 40 kind of behavior? Well, that's because we've only got 40. We've got 20 for each order, and we end up using one of the 20s over here and one of the 20s over here. So a first order circuit, we can't even get a bandpass filter. So if you want 40 over here and 40 over here, you're going to need a fourth order bandpass filter. What we've seen here is a lot of really good insight into how circuits behave, and this behavior carries over into all sorts of types of systems, not just circuits. Thanks, and we'll see you in the next video.